Let's take a look at question 14 of RACE-0 from the Secureum Bootcamp. Here, once again, we have a contract snippet, and we once again have security concerns or potential security concerns, 4 of them, and we should select the security concerns that are real concerns in this snippet. So A says that there is potential out-of-gas exceptions due to unbounded external calls within a loop. So if we look at the code, we see that there's basically only one loop here. This for loop, which iterates through the recipients which are passed into this function. And there is indeed an external call to this ERC20 token, which comes from a storage variable. And it is unbounded because it basically iterates through all of the recipients. So this could be a huge amount of recipients, and it would iterate over all of the recipients and make an external call for every single one of them. And that would potentially lead to an out-of-gas error, basically. And that should generally be avoided, so it's not a good practice to do stuff like this. But in this specific case, it's not really that much of a problem, because the recipients array can simply be reduced in size here. We can simply call the pay rewards function again if it fails due to running out of gas, and we can just pass a few less recipients to it so that it actually does not run out of gas. Where this is really dangerous is when this list of recipients is actually a array that is part of the storage. So it is a storage array, and you call pay rewards, and then it tries to iterate over all recipients which are in storage. And that is problematic, because now if it fails because of too many recipients, and you cannot reduce the number of recipients anymore because maybe there's no function in it, maybe the recipients array is only additive and you can't take anyone from them, well, then we have a problem, because now it would basically be a denial of service, because it would always run out of gas while trying to iterate through all of the recipients. In this case, it's not that big of a deal, but it is still a potential security concern. Next, we have B, which says that there is a ERC20 approve race condition. So ERC20 and ERC20 tokens have an approve function with which you can give another person an allowance to make use of your tokens. But we don't really see allowances being used here at all. To use an allowance, you would have to use transfer from instead of transfer, and you would have to actually call approve here, but none of this happens here. So maybe let's just talk about what an approve race condition is first. And for that, I have Alice and Bob here. And let's say that Alice has 5,000 of these ERC20 tokens over here. And now she wants to call the approve function. She wants to call this approve function, basically giving Bob access to 500 of her tokens. So when she calls approve with to Bob, amount 500, what happens is that this ERC20 token will internally store the information that Alice has given Bob an allowance of 500 tokens. Now Bob could call the transfer function, the transfer from function, and say that he wants to transfer from Alice to himself, and he transfers all of it, for example. He could do that, and that would reduce, because he now used his allowance, that would reduce his allowance to 0. And that's totally fine, nothing bad happened here. Now, where the bad things happen is when Alice actually intends to change this approval. Let's say that Alice wants to change the approval, and she sends another transaction which would set Bob's allowance to, let's say, 250. So she intends to reduce the allowance that Bob has. Now Bob doesn't like that, but Bob was smart. He prepared a little script that was observing for Alice to do something like this. So his script that he built, it notices, oh, Alice is trying to reduce this amount. So Bob's script sees that, and what Bob's script does is that it quickly, before, so this happens, maybe I should draw this a little bit different. So let's say Alice's transaction is still on the way, and she wants to reduce Bob's allowance to 250, we said. 250. Now Bob's script sees that that is going to happen, and his script then quickly sends this transfer from, where he says, take everything from Alice that I can take and send it to me, 500. And because Alice's updated approved transaction hasn't arrived yet, this amount of 500 is still valid. So now that Bob transfers 500 of Alice's tokens to himself, he gets those 500 tokens. So now Bob has 500. She has 4,500. And the allowance is reduced to 0. And then Alice's updated approved transaction finally arrives, and what does it do? It sets Bob's allowance to 250, but Bob's actual allowance is now 0 because he has already used his entire allowance. But because she's setting it to 250, now he again has a new allowance of 250. So what Bob can do now is send another transaction very quickly after she updated that, and send himself again with transfer from once more 250. So now he gets another 250, and Alice loses another 250, even though she intended to reduce his allowance. He basically got the old allowance and the new allowance. So he got way more than he was supposed to get from Alice. And that is what an approve front-running issue basically is. But that's not the case here. And therefore, ERC20 approve race condition is not the case. Okay, next is C, unchecked return value of transfer. So we have supposedly transfer returns a value, and that is not being checked, assuming it returns a boolean or another value and does not revert on failure. So we are to assume that this token, which is being called here, does return some value, and that value is not being checked. Well, obviously it's not being checked. So according to the official ERC20 standard, transfer functions of ERC20s are supposed to return a boolean, true or false, depending on whether they succeeded or not. Now the problem is that many transfer functions of ERC20 tokens do not follow the standard correctly, and instead of returning true when they succeed, they return nothing. And instead of returning false if they don't succeed, they revert. And that's a little bit annoying. So in this case, we are to assume that this ERC20 token returns a boolean and it does not revert on failure. So what happens here currently is that a transfer, an ERC20 token transfer, could potentially fail, and because it wouldn't revert on fail, we don't notice the fact that some of these transfers might have failed. And that's not good. We want to know if something failed or not. So in this case, where this token is part of the storage, and we know what kind of token it is, and we know how it works, we know what kind of what we can expect from it when using the transfer function. Here it would be fine if we basically always do this check if true or else, basically. But if we don't know what kind of token we're dealing with, the best practice is to use something called safe ERC20. And with safe ERC20, we basically wrap these transfer calls. And the safe ERC20 library will take care of handling both the tokens that follow the standard and also the tokens that do not follow the standard. So with that, we wouldn't have to worry whether tokens follow the standard or not, basically, and that's very helpful. So the best practice, if you're not sure what kind of token you're going to end up with, is using safe ERC20, basically. So in this case, we're not checking it. We're not checking the return value, even though it has a return value, and that is a security concern, therefore C is true. Lastly, we have D, which is potential reverts due to mismatched lengths of recipients and amounts arrays. So we have recipients here, which is a address call data, an array of addresses in call data, and we have amounts, which is an array of integers in call data. Now the problem is that we could start iterating of the recipients, but there isn't actually enough amounts for all of the recipients, because there's no guarantee that amounts and recipients are of the same length. But as we can see here, this I, the iterator, is applied to both the recipients and the amounts. So potentially there are less amounts than recipients, and then this would throw an error. And that would basically would have wasted a lot of gas to reach the point where this finally happens. To make sure that the number of recipients and the number of amounts are the same, we should really add a short check, a short if condition, to make sure that those two are the same. So the potential reverts due to mismatched lengths of recipient and amount arrays is indeed true. And that's it.